Something is happening on the Sun right now that scientists are watching very closely. A region called AR4334 has erupted not once, not twice, but multiple times this week, and several of those explosions are headed directly toward Earth. This is the kind of solar behaviour that doesn't happen every day, and it's unfolding as we speak. Stay with me for the next several minutes. We're going to explore what AR4334 actually is, why it keeps erupting, what's travelling through space toward us right now, and what all of this means for you and the technology you rely on every day. This isn't about creating fear, it's about understanding something remarkable that's happening 93 million miles away, and how it connects to our lives here on Earth. Here's what makes this week unusual. Active regions on the Sun erupt all the time. That's normal solar behaviour. But when one particular region fires off explosion after explosion in rapid succession, and when multiple blasts are aimed in our direction, that's when scientists start paying closer attention. AR4334 has done exactly that. It's been like watching a cosmic machine gun, with each burst sending energy and material hurtling through the solar system. If you're curious about space, about the forces that shape our technological world, or about the invisible connections between the Sun and Earth, then this is exactly where you need to be right now. Hit the like button if you want to understand what's really happening above our atmosphere. Subscribe if you're the kind of person who wants to know how the universe works, not just what's trending. And drop a comment telling me where you're watching from, because space weather affects different parts of the planet in different ways, and I'm genuinely curious where this information is reaching you. Let me be clear about something from the start. We're talking about a natural space weather event. We're not talking about the end of anything. What we're talking about is real science, real events, and real implications. The Sun is a dynamic star, and we live in its atmosphere. Everything that happens there eventually touches us here. Understanding that connection isn't about fear, it's about awareness. It's about respecting the power of natural forces and knowing how they weave into the fabric of modern life. AR4334 first caught attention because of its magnetic complexity. Sunspots aren't just dark patches on the solar surface. They're regions where powerful magnetic fields break through, creating conditions that can be incredibly unstable. Think of them as pressure points, places where the Sun's internal energy is trying to escape. Some sunspots stay relatively quiet, others become active, releasing flares and explosions. AR4334 fell into the second category, and it did so with remarkable consistency this week. The first eruption happened early in the week. Scientists monitoring the Sun noticed the sudden brightening, the surge of X-rays, the characteristic signature of a solar flare. They noted it, catalogued it, and continued their observations. Then it happened again and again. By the middle of the week, AR4334 had established a pattern. It wasn't settling down, it was ramping up. Each eruption added to the story. And with each one, the question became more pressing. What is this region going to do next? Then came the filament eruption. This wasn't just another flare. This was a massive structure. A twisted rope of plasma suspended in the Sun's atmosphere, suddenly destabilizing and exploding outward. When that happened, it launched an enormous amount of material into space, a coronal mass ejection, and the trajectory calculations showed something important. It was Earth-directed. But that wasn't the only one. Several of AR4334's eruptions this week produced CMEs. Several of those CMEs were aimed in our general direction, and here's where it gets even more interesting. When multiple CMEs travel through space in the same direction, they can interact, they can merge, they can amplify each other's effects. So what we have heading toward Earth right now isn't just one isolated blast of solar material. It's potentially a combined wave, a merged shockwave carrying the energy of multiple events. The arrival window is late today, possibly extending into early tomorrow. That means right now, as you're watching this, charged particles and magnetic fields from the Sun are racing through the inner solar system. They're covering the distance between the Sun and Earth at speeds of hundreds of miles per second. And when they arrive, they'll collide with Earth's magnetic field, triggering effects that range from beautiful to disruptive. This is why I wanted to make this video now, this week, while it's happening. Space weather isn't something that only matters to scientists. It matters to anyone who uses GPS, anyone who relies on satellites for communication, anyone who depends on stable power grids, anyone who's ever wanted to see the northern lights. In other words, it matters to all of us. We live in a technological civilization, and that civilization is affected by solar activity in minor ways. But being affected doesn't mean we're unprepared. Understanding what's happening gives us the ability to prepare, to adapt, to appreciate the scale of the forces we're dealing with. And that's what I want to do here. I want to walk you through this event step by step, not as a disaster story, but as a detective story, a mystery unfolding in real time, with clues scattered across 93 million miles of space, and with consequences that touch every corner of modern life. AR4334 is still on the sun's surface right now. It's rotating with the sun, moving across the solar disk as our star turns. Will it erupt again? Will it produce more Earth-directed CMEs? Or has it exhausted its magnetic energy for now? These are questions that scientists are asking as they monitor the region continuously. Solar activity isn't perfectly predictable. We can see the conditions that make eruptions likely, but we can't always say exactly when or how powerful they'll be. What we can do is watch. We can track. We can analyse, and we can understand. That's the remarkable thing about living in this era. We have spacecraft positioned between the Sun and Earth, constantly measuring the solar wind, detecting CMEs as they approach, giving us advance warning of geomagnetic storms. We have magnetometers scattered across the planet, measuring the strength and direction of Earth's magnetic field as it responds to solar impacts. We have satellites monitoring the Sun's surface in multiple wavelengths, capturing eruptions as they happen. So when AR4334 erupts, we see it. When it launches a CME, we track it. When that CME approaches Earth, we know it's coming. This knowledge doesn't eliminate the effects, but it gives us time to prepare critical infrastructure, time to reroute aircraft away from polar regions where radiation exposure increases during storms, time to alert satellite operators to protect their equipment, time for photographers and aurora enthusiasts to get ready for potential displays. This week's events are a reminder that we live in a connected solar system. The sun isn't some distant, unchanging ball of light. It's a dynamic, turbulent, powerful star that constantly shapes the space around it. Earth exists within that space. We orbit through the sun's extended atmosphere, through the solar wind, through the magnetic fields and particle streams that flow outward from our star. Most of the time, Earth's magnetic field shields us beautifully. But when a strong CME hits, that shield gets compressed, disturbed, energized, and that disturbance cascades through multiple systems. That's the story I want to tell you. Not just what happened, but why it happened, what it means, and how it connects to the bigger picture of our relationship with the sun. We're going to look at AR4334 in detail, understand its eruptions, track what's heading toward Earth, explore the impacts when it arrives, and then zoom out to see how all of this fits into the larger pattern of solar activity that's been building through this year. You're here because you're curious. You're here because you want to understand. That puts you ahead of most people, because most people never think about the sun except as a source of light and warmth. They don't realise it's also a source of storms. They don't know that solar weather affects Earth just as surely as atmospheric weather does. They don't understand that the space between the sun and Earth isn't empty. It's filled with energy, with particles, with magnetic fields, and with ongoing interactions that shape our technological environment. By the end of this journey, you'll understand all of that. You'll understand what makes AR4334 special. You'll understand why it kept erupting. You'll understand what's coming toward Earth and what happens when it arrives. You'll understand the broader context of where we are in the solar cycle and why this year has been particularly active. And you'll understand what all of this means for you, practically speaking, in your daily life. So let's begin where every good investigation begins, with the subject itself, with AR4334, because before we can understand what it did, we need to understand what it is. And that's exactly where we're going next. Every sunspot has a story, but not every sunspot becomes noteworthy. AR4334 earned its place in this week's headlines by doing what only certain regions can do. It became consistently active at exactly the right time, and in exactly the right position to affect Earth. But to understand why that matters, we need to start with the basics. What is a sunspot? What makes one region different from another? And what was special about this particular patch on the sun's surface? Imagine the sun as a sphere of roiling superheated gas, constantly churning with internal motion. Beneath the visible surface, massive currents of plasma circulate, carrying heat from the core outward. These currents also carry something else: magnetic fields. The Sun's magnetic field isn't simple or uniform. It's twisted, tangled, and incredibly powerful. In some places, these magnetic fields become so concentrated that they break through the surface, creating what we see as sunspots. A sunspot looks dark because it's cooler than the surrounding material. Not cold, of course. A sunspot is still thousands of degrees. But compared to the blazing heat of the normal solar surface, it appears darker. That darkness is a visual clue to what's really happening there. The magnetic field is so strong that it suppresses the normal convection process that brings heat to the surface. The region becomes magnetically dominated, and that dominance creates instability. AR4334 appeared in early January. It rotated into view as the Sun turned, revealing itself on the Earth-facing side of the solar disk. Solar observers track these regions carefully, cataloguing them with designations that start with AR for active region, followed by a number. The number tells you the order in which regions were identified. AR4334 was the 4,334th active region catalogued in the current numbering system. Location matters enormously in solar physics. A sunspot on the far side of the Sun, facing away from Earth, can erupt all at once without affecting us. But a sunspot near the centre of the visible disk, facing directly toward Earth, has a clear shot at our planet. AR4334 emerged in a favourable position, and it stayed there as the Sun's rotation carried it across the disk. For several days this week, it was aimed almost directly at us. Size tells part of the story, but not all of it. Some enormous sunspot groups remain relatively quiet. Some smaller regions produce significant activity. What matters more than raw size is magnetic complexity. How twisted are the field lines? How much energy is stored in the magnetic structure? How unstable is the configuration? These are the factors that determine whether a region will erupt and how powerful those eruptions might be. AR4334 showed complexity from the beginning. Observers could see multiple magnetic polarities tangled together, field lines crossing and interacting in ways that stored enormous amounts of energy. Think of it like winding up a spring. The more you twist it, the more energy you store. Eventually, that energy has to go somewhere. In a sunspot, that release comes in the form of solar flares and coronal mass ejections. The magnetic field in AR4334 wasn't static. It evolved throughout the week, changing configuration, building stress, finding new unstable arrangements. Each time it released energy through an eruption, the field would reorganize. Sometimes that reorganization led to stability. Sometimes it led to even more instability. This week, AR4334 kept finding ways to be unstable. Solar physicists have tools to measure these magnetic fields from Earth. They can map the strength and direction of the field across the solar surface. They can identify configurations that are particularly prone to erupting. When they looked at AR4334, they saw warning signs. They saw the kind of magnetic structure that has a history of producing activity. But seeing the potential for eruptions is different from knowing when or how many will occur. What makes a region like AR4334 noteworthy isn't the sunspot itself. Sunspots don't directly harm Earth. What matters is what they can produce. Solar flares, which are sudden releases of electromagnetic radiation, can affect radio communications and satellites. Coronal mass ejections, which are explosive releases of plasma and magnetic field, can trigger geomagnetic storms when they hit Earth. AR4334 was capable of producing both, and this week it did so repeatedly. The timing of AR4334's appearance wasn't coincidental. We're in an active phase of the solar cycle, a time when sunspots are common and solar activity is elevated. But even within an active phase, some regions stand out. AR4334 stood out not because it was the largest or the most complex region ever observed, but because it was active at the right time, in the right place, with the right magnetic structure to make an impact. Understanding this helps us appreciate what came next. AR4334 wasn't a fluke. It wasn't random. It was a natural consequence of solar processes, a region that developed the conditions necessary for repeated eruptions. The Sun creates dozens of active regions every year. Most of them produce a few flares and fade away. Some, like AR4334, become more memorable. They become the regions that remind us of the Sun's power and our connection to its natural cycles. So now we know what AR4334 is. It's a magnetically complex active region that appeared at the right time and place to affect Earth. It's a pressure point on the solar surface, where enormous amounts of energy were stored and waiting to be released. And this week, that release happened not once, but multiple times. The question now becomes, What exactly did AR4334 do? How did those eruptions unfold? What was the sequence of events that led us to this moment, with solar material racing toward Earth? That's the timeline we need to explore next, because understanding when and how AR4334 erupted gives us the full picture of what's heading our way right now. The first eruption came quietly, in the sense that it didn't immediately dominate headlines. It was early in the week, and AR4334 had just rotated into a position where Earth-facing eruptions were possible. Solar observers saw the telltale signs: a sudden brightening in X-ray emissions, a spike in ultraviolet light, the characteristic signature of magnetic energy being converted into radiation. A flare had occurred. Scientists noted it, classified it, and continued monitoring. Flares happen frequently on an active sun. During solar maximum and the years surrounding it, multiple flares occur every day across the solar surface. Most are small, some are moderate, a few are large. This first flare from AR4334 was moderate, enough to catch attention but not enough to raise alarms. What made it interesting was what it represented, the first sign that this region wasn't going to stay quiet. Then came the second eruption. Less than a day later, AR4334 flared again. This time, observers started to notice a pattern. 2 eruptions in rapid succession from the same region suggested ongoing instability. The magnetic field wasn't settling down after releasing energy. It was finding new ways to erupt. Solar physicists began paying closer attention to AR4334's magnetic structure, looking for clues about what might happen next. The third eruption confirmed that this wasn't a coincidence. AR4334 was in an active phase, repeatedly releasing stored magnetic energy. Each flare followed a similar pattern: a sudden brightening, a peak in intensity, then a gradual decline. But between eruptions, the region would rebuild. The magnetic field would twist again, store energy again, prepare for another release. It was like watching a cycle, a rhythm of tension and release playing out on the sun's surface. By midweek, AR4334 had erupted 4 times. That frequency is unusual even for an active region. Most sunspots that produce flares do so with longer intervals between events, sometimes days apart. AR4334 was erupting every several hours, maintaining a pace that suggested deep instability in its magnetic structure. Scientists monitoring the sun started discussing the region in their communications, sharing data, comparing observations, trying to understand what was driving this persistent activity. But here's what made AR4334's eruptions particularly significant. Several of them were accompanied by coronal mass ejections. Not every flare launches a CME. Many flares are confined, meaning the energy is released, but the material stays bound to the sun. CME-producing flares are different. They involve a more dramatic restructuring of the magnetic field, one that allows plasma and magnetic fields to escape the sun entirely and travel outward through the solar system. The first CME from AR4334 this week was detected by spacecraft positioned between the Sun and Earth. These spacecraft, designed specifically to monitor solar activity, saw the characteristic brightening and expansion of a CME leaving the Sun's atmosphere. They measured its speed, analysed its trajectory, and determined something crucial: it was heading in Earth's direction. Not a direct hit, perhaps, but close enough that Earth would likely intersect part of the CME's structure when it arrived. The second CME followed shortly after. Another eruption, another explosive release of material, another Earth-directed trajectory. Now scientists had multiple CMEs to track, each travelling through space at different speeds, each carrying magnetic fields and charged particles. The question became, would these CMEs arrive separately or together? Would they interact in space? Would they merge into a single, stronger disturbance? By the time AR4334 produced its 5th and 6th eruptions, the pattern was unmistakable. This region was in a highly unstable state, repeatedly finding ways to release energy. Each eruption drained some of the magnetic tension, but not enough to stop the cycle. The field would reorganize, build new stress, and erupt again. It was as if AR4334 had found a feedback loop, a configuration that allowed it to be persistently active rather than settling down after 1 or 2 major events. Then came the filament eruption. This was different from the flares that had preceded it. A solar filament is a structure of cool plasma suspended in the sun's hot atmosphere, held in place by magnetic fields. Filaments can persist for days or weeks, arching above the solar surface in elegant loops and curves, but they're inherently unstable. When the magnetic field supporting a filament changes, the filament can destabilize and erupt. AR4334 had a prominent filament associated with it, a structure that observers had been watching carefully. When that filament finally erupted, it did so dramatically. The structure unraveled, the plasma exploded outward, and an enormous CME was launched. This wasn't a small event. This was a major ejection, one of the largest of the week, and its trajectory was almost directly earthward. Spacecraft detected the filament CME immediately. It appeared as a bright, expanding halo in coronagraph images, a sign that material was travelling toward the observing spacecraft, and, by extension, toward Earth. Scientists calculated its speed and estimated its arrival time. Late on the 10th, possibly extending into the 11th. That gave Earth about 2 days' warning, enough time to alert relevant agencies and prepare for the geomagnetic storm that would likely result. But the filament eruption wasn't the end of AR4334's activity. The region continued to flare even after the filament was gone. More eruptions followed, smaller than the filament event, but still significant. Each one added to the total amount of energy and material that AR4334 had expelled this week. Each one contributed to the complex space weather environment developing between the Sun and Earth. By the end of the week, AR4334 had produced at least 7 distinct eruptions, several of which launched CMEs toward Earth. The exact count depends on how you classify smaller flares and whether you count events that occurred in rapid succession as separate eruptions or as one extended event. But the bottom line was clear. AR4334 had been extraordinarily active, and its activity had consequences for Earth. Now, as these CMEs travel through space, they're being tracked continuously. Scientists know approximately where they are, how fast they're moving, and when they're likely to arrive. The predictions are based on decades of experience with solar storms, on models that simulate how CMEs propagate through the solar wind, and on real-time observations from spacecraft that can see these structures approaching. What we're waiting for now is impact. The moment when these CMEs reach Earth and collide with our planet's magnetic field, that's when the geomagnetic storm will begin. That's when the effects will be felt, from auroras in the sky to potential disruptions in technology. But before we get to that impact, we need to understand what's actually travelling toward us. What is a CME, really? What does it carry? How does it interact with Earth? That's the next piece of the puzzle, and it's where the story shifts from what happened on the Sun to what's happening right now in the space between the Sun and Earth. Imagine billions of tons of superheated plasma, electrically charged and magnetically active, exploding off the surface of the Sun and racing through space at speeds that can exceed 1 million miles per hour. That's a coronal mass ejection. It's not fire, it's not a physical projectile. It's a cloud of particles and magnetic fields, expanding as it travels, carrying the Sun's influence outward through the solar system. When AR4334 erupted multiple times this week, several of those eruptions launched CMEs, and several of those CMEs are now on their way to Earth. Let's be clear about what a CME actually is, because the term gets thrown around without always being explained. The Sun's outer atmosphere, called the corona, is incredibly hot, millions of degrees. At those temperatures, atoms are stripped of their electrons, creating what's called plasma. This plasma is threaded with magnetic fields that originate deep inside the Sun. Normally, the corona is relatively stable, with plasma confined by these magnetic fields. But when a magnetic structure becomes unstable, it can explode outward, taking plasma with it. That explosion is a CME. What makes CMEs significant is what they carry. They carry mass, enormous amounts of solar plasma that become part of the solar wind. They carry energy, kinetic energy from their motion, and thermal energy from the heat of the plasma, and critically, they carry magnetic fields. Those magnetic fields are what make CMEs capable of affecting Earth, because when a CME hits our planet, it's the interaction between the CME's magnetic field and Earth's magnetic field that drives the geomagnetic storm. The CMEs from AR4334 this week were launched at different times, with different speeds, and with slightly different trajectories. The early ones were smaller, faster, and travelled at angles that would cause them to graze Earth's magnetic field, rather than hit it directly. The later ones, particularly the filament CME, were larger, more directly aimed, and carried stronger magnetic fields. All of these factors determine how powerful the resulting geomagnetic storm will be. Here's where it gets even more interesting. When multiple CMEs travel through space in the same general direction, they don't necessarily remain separate. The faster ones can catch up to the slower ones, They can collide, merge, and form a single larger disturbance. This phenomenon is called CME interaction, and it can significantly amplify the effects when the merged structure reaches Earth. Scientists tracking this week's CMEs are watching carefully to see if and how they interact before arrival. The journey from Sun to Earth takes time, even at speeds of hundreds of miles per second. Covering 93 million miles requires about 2 to 3 days for a typical CME. That travel time is both a blessing and a challenge. It's a blessing because it gives us warning. We can see the CME leave the Sun, track its progress, and predict when it will arrive. It's a challenge because conditions can change during the journey. The solar wind environment between the Sun and Earth isn't uniform. Variations in density and magnetic field can steer a CME, slow it down, or speed it up. Spacecraft positioned at what's called the L1 point, about 1 million miles from Earth toward the Sun, serve as sentinels. They sit in the solar wind, measuring its properties continuously. When a CME arrives at L1, these spacecraft detect it immediately. They measure the sudden increase in particle density, the change in magnetic field strength and direction, and the spike in solar wind speed. That data is transmitted to Earth in real time, giving us about an hour's notice before the CME hits Earth's magnetic field. The CMEs from AR4334 are in that space right now. They've left the Sun, they've been detected and tracked, and they're approaching Earth. The leading edge of the first CME may already be near the L1 point, with others following behind. Scientists monitoring the data from L1 spacecraft are watching for the telltale signs of arrival: the shock wave that precedes the main body of the CME, the compression of the solar wind, the rotation of the magnetic field. What happens next depends critically on the orientation of the CME's magnetic field. Earth's magnetic field points northward at the poles. If a CME arrives with its magnetic field pointing southward, the two fields can connect through a process called magnetic reconnection. That connection allows energy and particles from the CME to enter Earth's magnetosphere, driving the geomagnetic storm. If the CME's field points northward, matching Earth's field, the two fields don't connect as easily, and the storm is weaker. We won't know the magnetic field orientation until the CME actually arrives at L1. That's one of the uncertainties in space weather forecasting. We can predict when a CME will arrive and estimate its speed and density, but the magnetic field orientation can only be measured directly. So there's always an element of waiting, of watching the data come in, of seeing whether the conditions will be favourable for a strong storm or not. The filament CME is the one scientists are watching most closely. Filament eruptions often produce CMEs with complex magnetic structures, ones that can drive significant geomagnetic disturbances. The fact that this eruption was Earth-directed and occurred late in the week means its effects could be felt most strongly. If its magnetic field is oriented favourably when it hits, we could see geomagnetic storm levels higher than the initial predictions suggested. But even without perfect magnetic alignment, multiple CMEs arriving in succession can have cumulative effects. The first CME compresses Earth's magnetosphere, creating conditions that make subsequent impacts more effective. It's like waves hitting a beach. The first wave changes the shore, and the next wave can reach farther inland because of that initial change. Similarly, sequential CMEs can drive more intense storms than a single CME alone. This is why the clustering of eruptions from AR4334 matters. It's not just that one region produced multiple CMEs. It's that those CMEs were produced close together in time, meaning they'll arrive close together, meaning their effects will overlap and potentially amplify. Earth's magnetosphere won't have time to fully recover from the first impact before the next one hits. That sustained disturbance is what can push a minor storm into a moderate one, or a moderate storm into a strong one. The technical classification for the expected storm is G1, possibly reaching G2. That's on a scale where G1 is minor, G2 is moderate, and the scale goes up to G5 for extreme storms. The prediction of G1 to G2 is based on the observed properties of the CMEs, their expected arrival times, and statistical models of how similar events have affected Earth in the past. It's an educated forecast, but space weather forecasting isn't an exact science. There's room for the storm to be weaker or stronger than predicted. What we can say with confidence is that impact is coming. The CMEs are on their way. They will reach Earth. The magnetosphere will respond. And when it does, we'll see the consequences both in the sky and in our technology. But to understand those consequences fully, we need to shift our focus from space to Earth itself, to the magnetic shield that protects us, and what happens when that shield gets disturbed. That's the story of Earth's response to solar assault. And it's where the practical implications of this week's events become clear. So let's bring the story home. Let's talk about what happens when billions of tons of solar plasma slam into Earth's magnetic field, and how that collision creates effects we can see, measure, and sometimes feel in our daily lives. Earth has a secret weapon against the sun's fury, and most people never think about it. It's called the magnetosphere, a vast magnetic bubble that surrounds our planet, generated by the churning motion of molten iron in Earth's core. This magnetic field extends tens of thousands of miles into space, far beyond the orbit of satellites, creating a protective shield that deflects most of the solar wind. Without it, Earth would be constantly bombarded by charged particles, and life as we know it would be impossible. But the magnetosphere isn't impenetrable. When a powerful CME hits, that shield gets compressed, disturbed, and energized. That's when we experience a geomagnetic storm. Picture the magnetosphere as a bubble being pressed by the solar wind. On the side facing the sun, the bubble is compressed, pushed inward by the pressure of particles streaming from our star. On the night side, the bubble stretches outward into a long tail. Normally, this is a stable configuration. The solar wind pressure is constant, and the magnetosphere maintains its shape. But when a CME arrives, the pressure suddenly increases. The bubble gets squeezed harder. The magnetic field lines connecting Earth to space get stretched and tangled. Energy builds up in the magnetosphere, looking for a way to dissipate. That energy finds several outlets. One of the most visible is the aurora. When charged particles from the CME enter the magnetosphere, they spiral along Earth's magnetic field lines toward the poles. As these particles collide with atoms in the upper atmosphere, they transfer energy, causing those atoms to emit light. Oxygen atoms produce green and red colours. Nitrogen produces blue and purple. The result is the shimmering, dancing curtains of light we call the northern and southern lights. During a geomagnetic storm, auroras become brighter, more dynamic, and visible at lower latitudes than usual. For this week's event, aurora forecasts suggest visibility could extend well beyond the typical polar regions. People in northern tier states, across Canada and throughout Scandinavia, have a good chance of seeing displays if skies are clear. Depending on the storm's intensity, auroras might push even farther south, potentially visible from locations that rarely see them. That's one of the positive aspects of geomagnetic storms. They bring the cosmic light show to millions of people who would otherwise never experience it. But auroras are just the visible symptom of deeper electromagnetic disturbances. The same energy that creates those beautiful lights also creates currents in Earth's atmosphere and on the surface. These geomagnetically induced currents can flow through power lines, pipelines, and other long conductive structures. In extreme cases, they can damage transformers and cause blackouts. For a G1 storm, that risk is minimal. The induced currents will be weak, unlikely to cause any significant problems. But the potential is there, and it's something grid operators monitor during every geomagnetic storm. Satellites are more vulnerable. They orbit above most of Earth's atmosphere, in regions where the magnetosphere's protection is weaker. During a geomagnetic storm, satellites experience increased drag as the upper atmosphere heats and expands. They're also exposed to higher levels of radiation from the energized particles swirling through the magnetosphere. Most modern satellites are designed to withstand these conditions. They have shielded electronics, redundant systems, and protocols for safe mode if conditions become too severe. But older satellites, or those with less robust designs, can experience malfunctions. GPS satellites, which provide the positioning signals that billions of devices rely on, are particularly sensitive to space weather. During a geomagnetic storm, the ionosphere, a layer of Earth's atmosphere filled with charged particles, becomes disturbed. GPS signals travel through the ionosphere, and disturbances there can cause errors in position calculations. The errors are usually small, a matter of meters rather than kilometers, but for applications requiring high precision, those errors can matter. Aviation, surveying, autonomous vehicles, and financial systems that rely on GPS for time synchronization can all be affected. Radio communication also takes a hit. High-frequency radio waves bounce off the ionosphere, allowing signals to travel long distances by skipping between Earth's surface and the ionosphere. During a geomagnetic storm, the ionosphere's properties change. Some frequencies that normally propagate well become absorbed or scattered. Communications become unreliable. Amateur radio operators, maritime communications, and aviation radio traffic, especially on polar routes, can experience disruptions. For a G1 storm, these effects are mild. For stronger storms, they can be significant. Then there's the question of human health. Astronauts on the International Space Station or any future missions beyond low Earth orbit face increased radiation exposure during solar storms. Earth's magnetosphere provides substantial protection even at the station's orbital altitude, but the protection isn't perfect. During major events, astronauts may be instructed to move to more shielded areas of the station. For people on Earth's surface, there's no direct health risk. The atmosphere and magnetosphere together provide more than enough shielding. High-altitude flights, especially over polar regions, do experience slightly elevated radiation levels during storms, but the increase is small, comparable to the variation you'd experience from flying at different altitudes. The classification system for geomagnetic storms helps communicate these risks. G1 storms, like what's expected from this week's CMEs, are minor. They cause weak power grid fluctuations, minor impacts on satellite operations, possible aurora visible at high latitudes, and minimal effects on most technology. G2 storms, which is the upper end of what might occur if conditions align perfectly, add the possibility of aurora at mid-latitudes, voltage alarms on power systems, and more noticeable GPS errors. The scale goes up to G5, extreme storms that can cause widespread power blackouts, satellite damage, and complete loss of high-frequency radio communication. We're nowhere near that level with this event. Context matters here. The strongest geomagnetic storm in modern recorded history occurred in March of 1918. It was a G5 event that knocked out power across Quebec, damaged transformers, and caused aurora visible as far south as Texas and Florida. Before that, the Carrington event of 1815 was even stronger, causing telegraph systems to fail and setting telegraph paper on fire. These are the kinds of storms that define the extreme end of space weather. What's heading toward Earth right now is orders of magnitude weaker, but that doesn't mean we should ignore it. Even minor storms have effects, and understanding those effects helps us appreciate both the vulnerability and the resilience of modern technology. We've built a civilization that depends on satellites, GPS, power grids, and radio communications. All of these systems are designed with space weather in mind, with margins of safety and backup systems. Most of the time, those safeguards are more than adequate. But occasionally, the sun reminds us that we live in its atmosphere, and what happens 93 million miles away can touch us here. The arrival of the CMEs will be monitored in real time. Scientists will watch the data from L1 spacecraft, looking for the shock wave, the density increase, the magnetic field rotation. They'll issue alerts to power companies, satellite operators, airlines, and communication services. Those organizations will implement their protocols, the ones they've practiced and refined over years of dealing with space weather. For most people, life will continue normally. Phones will work, power will stay on, GPS will function, perhaps with slightly lower precision. But photographers will be watching the sky, aurora enthusiasts will be ready with their cameras, and scientists will be collecting data, adding this event to the long record of Earth's interaction with the Sun. What makes this week's event notable isn't its severity, it's the pattern it represents. AR4334 erupted multiple times in quick succession, producing multiple Earth-directed CMEs during an already active period of the solar cycle. This clustering, this rapid-fire sequence, is what catches attention. It's a reminder that solar activity comes in bursts, that active regions can dominate space weather for days or weeks, and that understanding these patterns helps us prepare for what might come next. Which brings us to an important question. Why did AR4334 keep erupting? What made this region so persistently unstable? Understanding the answer takes us deeper into solar physics, into the magnetic structures that drive these events. And that's where we need to go next to complete the picture of what happened this week. The Sun doesn't erupt randomly. Every flare, every CME, every burst of energy has a cause rooted in magnetic physics. To understand why AR4334 erupted multiple times this week, we need to understand what sunspots really are and how their magnetic fields store and release energy. The story of AR4334's activity is fundamentally a story about magnetism, about twisted fields and unstable configurations, about energy that builds until it finds a way to escape. Start with this idea. Magnetic fields are invisible. but they're real and physical. They exert forces, they store energy, and they can be twisted and stretched like rubber bands. Inside the Sun, these magnetic fields are generated by the motion of electrically conductive plasma. The Sun rotates, but not uniformly. The equator spins faster than the poles, creating a differential rotation that stretches and twists the internal magnetic field. Over time, these twisted fields become tangled, concentrated, and incredibly strong. When a bundle of magnetic field lines becomes twisted enough, it can rise to the surface, breaking through the photosphere and creating a sunspot. The magnetic field in a sunspot can be thousands of times stronger than Earth's magnetic field. That's enough to suppress the normal convection that brings heat to the surface, which is why sunspots appear dark. But more importantly, that concentrated magnetic field stores enormous amounts of energy, and like any system storing energy, it's looking for a way to release it. AR4334's magnetic field wasn't simple. Observations showed a complex structure with multiple magnetic polarities close together. In the simplest sunspots, you have a clear North Pole and South Pole with field lines arching smoothly between them. But in complex regions like AR4334, you might have north-south patterns close together, with field lines crossing, tangling, and creating zones of intense magnetic stress. These crossings are where the action happens. When magnetic field lines with opposite orientations come close together, they can reconnect. Imagine two rubber bands stretched in opposite directions, touching in the middle. If they suddenly swap connections, snapping into a new configuration, they release energy. That's magnetic reconnection. It converts stored magnetic energy into heat, light, and kinetic energy. On the Sun, magnetic reconnection is what powers solar flares. It's the fundamental process behind almost all solar eruptive activity. AR4334's complex magnetic structure meant there were multiple sites where reconnection could occur. Each time the field reconnected at one location, it would release energy, producing a flare. But that reconnection also changed the overall field configuration. Sometimes the change led to a more stable arrangement. Sometimes it led to an even more unstable one. This week, AR4334 seemed to keep finding unstable configurations. Think of it like a tangled knot. You can pull on one loop to loosen it, but sometimes that pulling just makes another part of the knot tighter. AR4334's magnetic field was undergoing a similar process. Each eruption was an attempt to untangle the field, to release stress, but the underlying twist was deep and persistent. The field would reorganize, find a new unstable spot, and erupt again. The filament that erupted later in the week was part of this story. Filaments are structures where cool plasma is suspended in the hot corona, held up by magnetic fields shaped like arches or channels. They can persist for days, looking stable, but internally they're often quite fragile. The magnetic field supporting a filament is in a delicate balance. If that balance is disturbed by a nearby flare or by the evolution of the underlying field, the filament can erupt. When AR4334's filament destabilized, it didn't just fall back to the surface. The magnetic field supporting it was connected to the larger structure of the active region. When the filament erupted, it carried that magnetic field with it, launching the large CME that's now heading toward Earth. That eruption was the release of a significant amount of stored magnetic energy that had been building in that structure for days. But even after the filament was gone, AR4334 continued to flare. That tells us the instability wasn't confined to the filament. The entire active region had a magnetic configuration prone to repeated eruptions. This kind of behaviour is characteristic of what solar physicists call magnetically complex regions. They're the ones that produce the majority of significant solar activity. They're the regions that space weather forecasters watch most carefully. What determines whether a region will be persistently active or settle down after one eruption? Several factors come into play. The amount of magnetic flux, which is a measure of the total magnetic field threading through the region, matters. More flux means more stored energy. The rate at which new magnetic field is emerging from below the surface also matters. If fresh magnetic field keeps pushing up, it can sustain activity by continuously adding new instabilities. And the history of the region matters. Regions that have erupted many times tend to keep erupting, because each eruption doesn't completely resolve the underlying magnetic stress. AR4334 checked all these boxes. It had substantial magnetic flux, it showed signs of ongoing magnetic emergence, and once it started erupting, it established a pattern of repeated activity. Scientists monitoring the region could see these characteristics in the data. They could identify the complex magnetic structures, the sites of ongoing reconnection, the potential for further eruptions. but predicting exactly when the next eruption would occur, or how powerful it would be, remained challenging. This is one of the frontiers of solar physics. We understand the general principles of how sunspots erupt. We can identify regions that are likely to produce activity, but forecasting specific events with precision is still difficult. The magnetic field evolves continuously in ways that are sensitive to small changes. A slight shift in one part of the field can trigger a cascade that leads to a major eruption, or it can lead to nothing. The challenge is similar to earthquake prediction. We know where the faults are, we know stress is building, but we can't say exactly when the next quake will happen. Despite these limitations, space weather forecasting has improved dramatically over the past few decades. We have better observations, more sophisticated models, and deeper understanding of the physics. When a region like AR4334 becomes active, forecasters can issue warnings, can estimate the likelihood of further eruptions, can track CMEs and predict their arrival at Earth. The forecasts aren't perfect, but they're good enough to be useful, good enough to give critical infrastructure operators the information they need to prepare. AR4334's story is far from unique. Every solar cycle produces dozens of active regions with complex magnetic fields. Many of them erupt multiple times. Some become famous, like the region that produced the Halloween storms of 2003, or the region that caused the 1989 Quebec blackout. Others, like AR4334, make headlines for a week and then fade from public attention as the sun's rotation carries them around to the far side. But each one adds to our understanding. Each one provides data that refines our models and improves our forecasts. The magnetic story of AR4334 is a microcosm of solar behaviour. It shows us how energy builds, how instabilities develop, how eruptions occur. It reminds us that the sun is a dynamic, ever-changing star, driven by processes that span scales from the microscopic interactions of particles to the global circulation of plasma. And it connects to the larger pattern of solar activity, the 11-year cycle that governs the ebb and flow of sunspots, flares, and storms. That larger pattern is the context we need to fully understand why this week mattered, and that's where we're headed next. AR4334's eruptions this week didn't happen in isolation. They're part of a larger story, one that spans years and encompasses the entire sun. That story is the solar cycle, the roughly 11-year rhythm of rising and falling solar activity. Understanding where we are in that cycle and what it means for the months ahead puts this week's events into proper perspective. It shows us that AR4334 is one chapter in an ongoing tale of how our star behaves and how that behaviour affects Earth. The solar cycle is driven by the sun's magnetic field, which flips polarity approximately every 11 years. During the quiet phase, called solar minimum, the sun has few sunspots and produces minimal flares and CMEs. As the cycle progresses towards solar maximum, sunspot numbers increase, active regions become more common, and eruptive activity rises. After maximum, activity gradually declines again toward the next minimum. The cycle isn't perfectly regular. Some cycles are stronger than others. Some have sharp peaks. Some have extended maxima with sustained high activity. We're currently in solar cycle 25, which began in late 2019. The cycle has been progressing more quickly than initial predictions suggested. Solar maximum, the peak of the cycle, occurred earlier than expected, and now, in early 2026, we're in what's called the declining phase. But declining doesn't mean quiet. Solar activity often remains high for several years after maximum, with frequent active regions and regular geomagnetic storms. That's the phase we're in now, and it's why regions like AR4334 are appearing with regularity. The sun today is dotted with active regions. AR4334 is just one of several currently visible on the Earth-facing hemisphere. Some are quiet, merely dark spots with stable magnetic fields. Others are showing signs of activity, small flares here and there. A few, like AR4334, are producing significant eruptions. This is typical for the post-maximum phase. The sun's magnetic field is still highly complex, still generating the conditions for sunspot formation and eruptive activity. But it's not just sunspots that contribute to space weather. Coronal holes, regions where the sun's magnetic field opens outward into space, also play a role. These holes allow high-speed streams of solar wind to escape, creating conditions that can trigger minor geomagnetic disturbances when Earth passes through them. Right now, there are several coronal holes on the sun, including some near the solar equator, where they're more likely to affect Earth. The combination of active regions and coronal holes creates a complex space weather environment. This layering of effects is important. Even without AR4334's CMEs, Earth would be experiencing enhanced solar wind conditions from the coronal holes. When you add the CMEs on top of that, the combined effect is stronger than either would be alone. It's like weather on Earth, where a cold front moving through during a rainstorm can create more severe conditions than either the front or the rain alone would produce. The pattern we're seeing in 2026 is one of sustained activity. There isn't a single dominant active region producing all the action, but rather a steady stream of regions appearing, erupting, and rotating out of view, while new regions emerge to take their place. This creates a background level of space weather that's elevated compared to solar minimum, but not catastrophic. Geomagnetic storms occur regularly, most of them minor, some moderate, with the occasional strong event mixed in. Comparing this to past cycles gives perspective. Solar cycle 24, which preceded the current cycle, was relatively weak. It had a subdued maximum and fewer major events than typical cycles. Cycle 23, before that, was stronger, producing several significant storms, including the Halloween storms of 2003. Cycle 25 appears to be somewhere in between, stronger than 24, but not as intense as 23. This means we should expect regular space weather activity, but not necessarily the extreme events that characterized earlier decades. Historical records show that solar activity has varied significantly over centuries. The Carrington event of 1815 occurred during a strong solar cycle. The mid-20th century saw several very active cycles. There have also been periods, like the Maunder minimum in the 17th century, when solar activity nearly ceased for decades. We're currently in a period of moderate to strong activity, within the normal range of solar behaviour. What does this mean for the rest of 2026 and beyond? We can expect continued active regions. Some will be small and quiet, others will be large and eruptive. The frequency of geomagnetic storms will remain elevated compared to solar minimum, but will gradually decline as we move further into the cycle's descending phase. By 2027 or 2028, activity should be noticeably lower. By 2030 or so, we'll approach the next solar minimum, when active regions become rare and space weather becomes quiet again. But between now and then, events like this week's will occur regularly. Not every week will see a region as active as AR4334, but every few months there will likely be a region that produces multiple eruptions, that launches Earth-directed CMEs, that triggers geomagnetic storms and creates auroras. This is the natural rhythm of living with an active star. It's something that past generations didn't worry about, because they didn't have the technology that's vulnerable to space weather. But for us, in this technological age, it's part of the landscape we navigate. Space weather forecasting has become a critical service, much like meteorological forecasting. Government agencies, private companies, and international collaborations work continuously to monitor the sun, track solar wind conditions, and predict space weather impacts. The data flows in real time from spacecraft and ground-based observatories. Models run constantly, updating predictions as new information arrives. Alerts are issued when significant events are expected. This entire system exists because we've recognised that space weather matters. The bigger picture, then, is this. AR4334 is one data point in an ongoing process. It's part of Solar Cycle 25's story, part of the pattern of activity that defines this phase of the cycle. It caught attention because of its rapid-fire eruptions and because multiple CMEs were Earth-directed. But it's not an anomaly. It's not a sign that something unusual is happening to the sun. It's simply solar physics in action, magnetic fields doing what magnetic fields do, energy finding its release through the spectacular violence of solar eruptions. Understanding this context helps us maintain perspective. The sun is powerful. Its eruptions can affect Earth. But these effects are manageable. We've learnt to live with space weather, to build our technology with it in mind, to monitor and predict it. AR4334's activity this week is a reminder to stay informed, to appreciate the connection between the sun and Earth, to respect the forces that shape our space environment. And it points us toward the practical question that matters most to people watching this video. What should you actually do with this information? That's what we need to address next, because understanding what's happening is valuable only if it translates into meaningful awareness or action. Knowledge without application is just information. You've learned about AR4334, about its eruptions, about the CMEs heading toward Earth, about geomagnetic storms and solar cycles. Now the question becomes, what does this mean for your actual life? How should this awareness change what you do, if at all? The answer depends on who you are and what you rely on, but there are practical considerations that apply to almost everyone. For most people, the honest answer is that you won't notice anything. Your phone will work, your power will stay on, your internet connection will remain stable. The infrastructure that supports modern life is designed to handle minor geomagnetic storms without significant disruption. Engineers know about space weather. They build margins of safety into power grids, satellite systems, and communication networks. For a G1 or even a G2 storm, those margins are more than adequate. Life continues normally, but there are exceptions. If you rely on high-precision GPS for work, you might notice reduced accuracy during the storm. Surveyors, precision agriculture systems, autonomous vehicle testing, these applications can see errors increase from a few centimetres to tens of centimetres or more. The degradation is temporary, lasting hours to a day, but it can affect operations that require absolute positioning accuracy. Being aware of a geomagnetic storm in progress allows you to adjust, to postpone critical measurements, or to apply correction factors if you have access to real-time GPS monitoring systems. Aviation is another area where awareness matters. Airlines already monitor space weather as part of their operational planning. During geomagnetic storms, they may reroute polar flights to lower latitudes to reduce crew and passenger radiation exposure. They may experience communication difficulties with planes flying over the poles, where high-frequency radio is less reliable. If you're a frequent traveller on polar routes, you might notice these adjustments, though most passengers never realise the reasons behind them. Satellite operators, both commercial and governmental, take active measures during storms. They might delay software updates or manoeuvres until after the storm passes. They monitor satellite health more closely, watching for anomalies caused by increased radiation or charging effects. For users of satellite services, this mostly happens in the background, invisible. But occasionally, satellite TV or internet services might experience brief disruptions. Knowing a storm is in progress helps explain these moments when the signal drops out temporarily. Amateur radio operators are uniquely affected by geomagnetic storms. High-frequency propagation, which depends on ionospheric reflection, changes dramatically during storms. Some bands that normally support long-distance communication become unusable. Other bands might open up in unexpected ways. For the ham radio community, space weather forecasts are essential planning tools. They check space weather conditions before attempting long-distance contacts, adjusting their expectations and strategies based on current conditions. Then there are the auroras. For people at high latitudes, northern lights are a regular occurrence, but geomagnetic storms make them brighter and more active. For people at mid-latitudes, storms offer a rare opportunity to see something they might witness only a few times in their lives. If you're anywhere from the northern states across Canada and into northern Europe, tonight and possibly tomorrow night could bring visible auroras if skies are clear. That's not a disruption, it's a gift. It's a chance to see the connection between Earth and Sun, made visible in ribbons of green and red light dancing across the sky. Aurora photography has become a passion for many. The combination of accessible camera technology and space weather forecasting has created a community of aurora chasers who monitor predictions closely and travel to dark sky locations when storms are expected. Social media fills with aurora photos during these events, each one a testament to the beauty of geomagnetic storms. If you're interested in trying to photograph auroras, this is your chance. Find a dark location away from city lights, point your camera north, use a long exposure, and see what appears. For most technology users, the practical implication is simply awareness. Understanding that space weather affects GPS, satellites, and radio communications helps explain occasional glitches that might otherwise seem mysterious. It provides context for news reports about geomagnetic storms. It connects abstract solar physics to tangible effects. That awareness doesn't require action, but it enriches understanding of the world we live in. There's also a broader implication about infrastructure resilience. The fact that we can experience geomagnetic storms regularly, without major disruptions, is a testament to good engineering and planning, but it's not guaranteed. Extreme storms, the G4 and G5 events that occur rarely, can overwhelm these protections. Power transformers can be damaged, satellites can fail, communication systems can go dark. These events are rare, happening perhaps once or twice per solar cycle, but they're possible. Understanding space weather helps us appreciate the need for continued investment in resilient infrastructure. Preparedness for extreme space weather is similar to preparedness for other low-probability, high-impact events. You don't live your life in fear of them, but you acknowledge they exist and support measures that reduce vulnerability. That might mean supporting grid modernization that includes space weather resilience. It might mean advocating for more space weather monitoring satellites. It might simply mean staying informed and understanding the risks. For this particular event, with AR4334's CMEs arriving, the practical advice is simple. If you want to see auroras, watch the forecasts, check aurora alert services, and look north if you're at a latitude where visibility is possible. If you work in a field affected by GPS precision or satellite communications, be aware that temporary disruptions might occur. If you're just curious about space weather, follow the real-time data, watch the measurements from the L1 spacecraft, and see how the predictions match the actual impacts. And if none of these apply to you, simply appreciate that you live in a time when we can track solar eruptions, predict their arrival at Earth, and understand the physics behind the connection. The practical implications are proportionate to the event. This isn't an emergency. It's not a crisis. It's a normal consequence of living with an active star during an active phase of the solar cycle. But it's a reminder that space isn't empty. The region between the Sun and Earth is filled with activity, with particles and fields and energy. Most of the time, we're shielded from those forces. But sometimes, when conditions align, we get a glimpse of the dynamic environment we inhabit. That glimpse can be beautiful, it can be scientifically fascinating, and it can occasionally be disruptive. Understanding all of that, seeing it in context, is what transforms abstract solar physics into personally relevant knowledge. And with that understanding in place, we can step back one more time, look at everything we've covered, and draw some final connections about what this week's events tell us about our relationship with the Sun and where this story goes from here. We've journeyed from a single active region on the Sun's surface to the space between the Sun and Earth, from magnetic physics to aurora displays, from eruption timelines to practical implications. AR4334's story this week has been a thread connecting all of these elements, showing us how solar activity cascades through multiple systems to touch our lives in ways both visible and invisible. But this story doesn't end with the arrival of this week's CMEs. It continues, as it has for billions of years and will for billions more, as the Sun breathes and pulses and occasionally roars. What happened this week matters not because it was unprecedented, but because it was characteristic. AR4334 behaved as magnetically complex active regions do. It stored energy, found instabilities, and released that energy through eruptions. Some of those eruptions were Earth-directed, triggering the chain of events that brings us to this moment. This is solar physics working exactly as we understand it. And that understanding is something we've built over decades of observation, of spacecraft missions, of theoretical work and computer modelling. Every event like this one adds to that knowledge. Scientists right now are watching the data streams from L1 spacecraft, waiting for the CMEs to arrive. When they do, there will be a spike in the measurements, a clear signature that solar material is washing over Earth's magnetosphere. That data will be analysed, compared to predictions, and used to refine future forecasts. The storm will be categorised, its impacts assessed, and its place in the historical record established. AR4334 will be remembered as one of many active regions that contributed to space weather during solar cycle 25, notable for its rapid sequence of eruptions, but not necessarily for exceptional intensity. As the Sun rotates, AR4334 is moving toward the western limb of the solar disk, heading toward the far side, where we can no longer see it directly. Will it continue erupting? Will it produce more CMEs that affect other planets, but miss Earth? These questions will be answered over the coming days, by observers tracking the region until it disappears from view. And while AR4334 fades, other regions will emerge. The Sun is never static. New active regions appear constantly, each with its own magnetic personality, each with potential to contribute to the ongoing story of solar activity. The broader narrative of solar cycle 25 continues as well. We're in a phase where space weather is a regular occurrence, where aurora enthusiasts have frequent opportunities, where space weather forecasters stay busy. This will persist for months and years as the cycle gradually winds down. But it will wind down. Activity will decline. By the end of the decade, we'll be approaching the next solar minimum, when the Sun goes quiet again and active regions become rare. And then, inevitably, the cycle will begin anew, building toward the next maximum in the mid-2030s. This cyclical pattern has repeated throughout human history, but only in recent decades have we had the technology to see it clearly and the infrastructure to be affected by it. Our ancestors witnessed auroras without understanding their cause. They saw sunspots with primitive telescopes, but couldn't predict their behaviour. We've gained so much knowledge, yet each solar cycle reveals new subtleties, new behaviours we didn't anticipate, new questions to investigate. The sun remains a subject of active research, a laboratory for plasma physics and magnetic field dynamics that we can observe but not directly access. What this week teaches us, beyond the specifics of AR4334, is the importance of sustained observation and understanding. We watch the sun not out of fear, but out of necessity and curiosity. We track space weather because it affects the technology we depend on, and because understanding it is simply fascinating. Every eruption, every CME, every geomagnetic storm is an experiment conducted by nature, showing us how stars behave, how magnetic fields interact, how energy propagates through plasma. AR4334's eruptions are data points in that grand experiment. For you watching this video, the takeaway can be as simple or as deep as you choose. Maybe it's just the awareness that the sun is active right now, that CMEs are on their way, that auroras might be visible tonight if you're in the right place. Maybe it's a deeper appreciation for the invisible forces that connect the sun to Earth, for the magnetic shield that protects us, for the technology we've built to monitor and predict space weather. Or maybe it's a spark of curiosity that will lead you to explore more, to follow space weather forecasts, to learn about solar physics, to become one of those people who understands that what happens in space matters here on Earth. The connection between the sun and Earth is fundamental. Life on this planet exists because of the sun's light and warmth. But that same star that enables life also produces storms that challenge our technology. It's a relationship of balance, of benefit and risk, of profound interconnection. We orbit through the sun's atmosphere, and we feel its moods. Understanding that relationship, respecting it, preparing for it, these are markers of a mature technological civilization. We're learning to live with our star, not just benefit from it. I want to thank you for staying with me through this exploration. We've covered a lot of ground, from the mechanics of sunspots to the beautiful complexity of auroras, from magnetic reconnection to practical GPS impacts. If you found value in this journey, if it helped you understand what's happening right now above our atmosphere, then do me a favour. Hit that subscribe button, because space weather doesn't stop with AR4334. There will be more active regions, more storms, more events worth exploring together. Hit the like button if this video gave you a new perspective on the sun and its effects on Earth. And most importantly, drop a comment. Tell me where you're watching from. Tell me if you've ever seen auroras. Tell me what surprised you most about this topic. Tell me if tonight's the night you're going to step outside and look north, hoping to catch a glimpse of the solar storm made visible in shimmering light. I read every comment, and I'm genuinely curious about where this information is reaching people and how it connects to your experiences. The story of AR4334 is one chapter in the ongoing narrative of humanity's relationship with the sun. That narrative stretches back to ancient astronomers watching sunspots through smoke-darkened glass, and forward to future missions that will send spacecraft closer to the sun than ever before, studying it in unprecedented detail. We're living in a remarkable moment in that story, with the tools to see, to understand, and to predict. We're not helpless before solar storms. We're informed. We're prepared. We're capable of living with the variability of our star while benefiting from its constancy. Tonight or tomorrow, when the CMEs arrive and the geomagnetic storm begins, remember what you've learned here. Remember that this is natural, predictable, and manageable. Remember that the auroras you might see are evidence of Earth's protective magnetosphere doing its job, channeling solar particles harmlessly into the upper atmosphere. Remember that the minor disruptions some systems might experience are vastly outweighed by the benefits of the technology we've built. And remember that the sun, 93 million miles away, is not some distant abstraction but an intimate part of our daily existence, connected to us by invisible threads of magnetism and light. AR4334 erupted multiple times this week. Several of those eruptions sent material toward Earth. That material is arriving now, and we're ready. We understand what's happening, we appreciate the beauty of the forces involved, and we continue the ongoing watch, monitoring our star, learning its patterns, and living wisely under its light. That's the story of this week, and it's a story that will continue as long as the sun shines and humans look up to understand what they see. Thank you for watching. Stay curious, look up, and I'll see you in the next exploration of the remarkable universe we inhabit.